over q, but x squared minus 3 and x squared minus 2 are irreducible. Okay? So check it out. So we can take q of x, right? In mod by the ideal generated by x squared minus 3. So this gives, if I look at this as a plus b alpha, right? To keep using my notation, then we have f of alpha equals to 0 since, alpha squared minus 3 is equal to 0, right? So what is this example? So this is really what? It's really just q adjoin square root of 3. Because alpha is serving as the square root of 3, because alpha squared is equal to 3. And similarly, if we looked at q of x mod the ideal generated by x squared minus 2, well, that is going to be up to isomorphism q adjoin the square root of 2, right? Where, let's say, beta is equal to 2, so that is making beta squared minus 2 equal to 0. Hence, f of beta is equal to 0. So this goes to show for a given polynomial, there may be different extension fields that you could look at, which would do what? I mean, each one of q adjoin square root of 2, q adjoin square root of 3, they both make f of, they both give you a 0, right? They adjoin a 0 for this polynomial, which is given. But they're also distinct, right? And by the way, you could look at q adjoin alpha and beta. In other words, q adjoin the square root of 2 and the square root of 3. That would be, what that means is the smallest field that includes the rational numbers as well as the square root of 2 and the square root of 3. In that field, so in this field, f of x factors completely, right? Because you can write f of x as x minus square root of 3, x plus root 3, x plus root 2, x minus root 2. So if you can find a field in which the polynomial factors completely, we call such fields a splitting field. So this makes it a notice that neither q adjoin root 3 or q adjoin root 2 on their lonesome are a splitting field because they don't make f of x factor completely. They leave you with x squared minus 2 or x squared minus 3. You need both of them to factor it completely. So to say a polynomial is split is to mean it's written as a product of linear polynomials, possibly repeated. So like every polynomial is split over the complex numbers because of the fundamental theorem of algebra. It says you can always factor over the complexes, right? But in the real numbers, we have irreducible quadratics. So like that x squared plus 4x plus 5 we were looking at a second ago, that would be, something that cannot be split over the reals. Now the complete discussion of splitting fields is something I would do when we talk about, say, Galois theory, which is not this semester. So you're safe. But it's really not that bad. All right, so it seems like we're due for a definition. Let E be extension field of F, all right? An element alpha in E is called algebraic over F if there exists non-zero f of x coefficients in F for which f of alpha is equal to 0. An element alpha in E, which is not algebraic, is called transcendental. Over F. So notice that algebraic and transcendental both, you have to refer to the base field. The term transcendental and algebraic without reference to the base field, not helpful. And yet people often use these words without reference to the base field, all right? Because they have a particular context in mind, which we'll get to here. Let's see here, so example 10. If we have alpha is in the field, right, then if we look at f of x equals to x minus alpha, that's an element of the polynomials over the field, and what? F of alpha equal to 0. So therefore, alpha is algebraic over F. Any element of a field is algebraic over that given field. Okay? A more interesting example, of course, is alpha equals to I, right? Which is an element of the complex numbers, is algebraic over the reals, right? Since what? F of x equal to x squared plus 1, right? That's a real polynomial such that f of I is I squared plus 1, right? Is 0. So the complex number, the imaginary unit I, is an algebraic element over the reals. And you notice that I could just as well, I could cross out the R and just as well put what there, Audric?
Cross out the R?
Yeah. Complex, right? I is also algebra. Like you could just as well put Q here and put Q here just the same, right? I is also algebraic.
This is our containment.
Yeah. Right? Yeah, I mean, because that is after all a rational polynomial. So it's like, I mean, yeah, there's a theorem to state there, but I'm not even getting at the theorem. I'm just saying, like, this is literally a polynomial with rational coefficients, so this proves it's, all right. Here's a little bit more, kind of a little bit more interesting example. Square root of 2 is algebraic over Q adjoin the square root of 3. Since x squared minus 2 is a polynomial with Q adjoin root 3 coefficients, and f of the square root of 2, of course, is 0 in this context. Again, you could also point out that square root of 2 is algebraic over q. We could drop the root 3. That's just kind of window dressing there. Here's one that is a little bit harder. Is if we look at example 13, the question basically is to look at the real number. Alpha is 2 plus the square root of 1 plus the square root of 3. Right? Show this is algebraic over q. How would we do it? How do you show a number is algebraic? You got to find a polynomial which takes it as a 0. How do you do that? Well, I'm going to give you advice I gave my algebra class this last week. Isolate the radical. And then what's the natural enemy of the square root? The square. Alpha squared minus, man, I wanted to buy my mom this ridiculous, like, Trump mug, because she really doesn't like Trump. She actually hates Trump pretty much, but the stupid, I found, like, Facebook keeps, like, advertising this thing to me, and it's like $21, and I was like, fine, I can't find anything else, I'll just buy it. So I click on it, I get in there, and it's like, and $6 more for shipping. I'm like, you're dead to me. I am not going to spend nearly $30 for a mug. Good grief, the shipping. That upset me. Anyway, 4 alpha. Plus 3, right? So we've isolated the radical again, and then we have to square again. So you got alpha to the 4th. Oh, I got to think about that. Rats.
Wait, why don't you factor it and then square it?
Oh, does that factor?
Pretty sure. -3 and -1. Right?
Sure. I mean, it's still, anyway, so I would do that, but I don't think that actually helps because I actually want the polynomial.
Oh.
You know what I'm after. So annoyingly, alpha to the 4th minus 4 alpha cubed plus 3 alpha squared minus 4 alpha squared 16 alpha squared minus 12 alpha plus 3 alpha squared minus 12 alpha plus 9. So we get alpha to the 4th minus 4 alpha cubed. What's that give me?
-1 -15,
Yeah, 18 alpha squared minus 24 alpha, right? Plus 6. So we can take the polynomial, f of x equal to x to the 4th minus 4x cubed plus 18x squared minus 24x plus 6. That is the polynomial with rational coefficients, which takes alpha as its 0, which shows you that alpha is algebraic. What's an example of a element which is not algebraic? If you look at pi. over q. Can you find any polynomial with rational coefficients which takes pi as its 0? In other words, can you, you know, it has to be finite, yeah. I mean, it's polynomial. Does there exist a collection of coefficients, finitely many, such that that linear combination of pi is equal to 0? No, because if there was,
That would be rational.
like you could solve this. I mean, there's various things that go on, but if you could solve that for a0, you know, so I don't know, like, I don't know how to prove it specifically, like right off the top of my head, but you can prove that pi is irrational, and I don't think this is actually an easy thing to prove, but you can prove that pi is not algebraic over the rationals. In fact, I don't think this is at all an easy thing to prove. This we could probably spend a whole class trying to prove carefully. Likewise, E over Q. Both pi and E are transcendental over Q. However, notice this, pi and E are algebraic over R. Any element of a field is algebraic over that field, by my example 10. So what do people mean when they say that pi is a transcendental number, or that E is a transcendental number? They're talking about with respect to the rational field. And that's the default that like number theorists will go with. But understand that those terms, algebraic and transcendental, they're a matter of perspective. Anyway, that's where we got to today. So thanks, guys. Hope you don't mind me interrupting the notes to like dig into examples.